So it's a pleasure to be here and to give these lectures. So I'm going to just give you a very basic overview, high-level overview of one particular fluid dynamics code that's designed for studying astrophysical problems called Athena. The algorithms in Athena are very similar to many of the algorithms in other codes. In fact, some that you've heard about already, like Ramsey's, and some that you'll hear about, I think, next week, Flash. And so I suspect that I'm going to overlap a lot with some of those lectures, especially today, since today I'm going to give you just an introduction. And so I apologize in advance if you already know all this stuff and you've seen it already. But on the flip side, I think that if you're not familiar with these kind of algorithms, then seeing this material presented more than once and perhaps in a different view from other lectures is a good thing, especially if you've been out all weekend, staying out late, hiking, doing wine tours, Monday morning, 9 a.m. You may not be ready for something very detailed and high level, getting to the guts right away. So I'm going to stick to, guess I shouldn't have touched that. What happened? Sorry about that. So I'm going to, as I say, begin at the beginning and give you a basic introduction. There we go. I don't know what happened.
All right. I am
you see?
so good. I just have to.
It's definitely Monday morning. The machine is afraid. All right. So what is Athena? Well, there's a fair bit of information online, and the best place to start is these track web pages. I'll tell you about track a little bit later. Okay, so that was supposed to bring up a browser, which there we go, kind of minimize. So here is the splash page for this track website. So what is Athena? Well, you can read it. It's a grid-based astrophysical MHD code designed primarily for studies of the ISM, accretion disks. It's freely available. You can download version 4.2, actually. This needs to be updated. It has algorithms for hydrodynamics and MHD in 1D, 2D, and 3D. Special relativistic hydrodynamics in MHD, probably not so useful for star formation, but it's in there. Ideal gas equation of state with any arbitrary gamma, including isothermal, which is a special case that can't be treated with just gamma 1. You have to do special things for that. Arbitrary number of passive scalars, that's very useful if you want to do chemistry, as we'll hear this afternoon, and you want to carry around many different chemical species. Then you can have an arbitrary number of chemical species that you can carry with the flow, self-gravity and the gravitational potential, ohmic resistivity, ambipolar diffusion, and the Hall effect, all important for star formation. Navier-Stokes and anisotropic Brzezinski viscosity, that's not so important for star formation, but useful for studies in weakly collisional plasmas. Isotropic, anisotropic thermal conduction, optically thin radiatively cooling. Those are all the physics options that are there in the public version. In addition, on the algorithm side, it has both Cartesian and cylindrical coordinates, static mesh refinement, as opposed to adaptive mesh refinement, and I'll have more to say about that tomorrow, where I talk more about the grids. Shearing box source terms, which are useful for studying turbulence in accretion disks in the shearing box approximation. And then finally, it's parallelized using MPI. So if you're going to run the code in parallel, you do need to have the MPI library installed on the machine. So then you can see there's a lot of stuff on here. The documentation page in particular has a tutorial, a user guide, a programmer guide. There's links to all the method papers that describe this in the literature. And there's even Doxygen documentation if you want to look at that as well. So this is the sort of place to go to. And there's a downloads page here where you can get a copy of the code. So if you're going to use it this afternoon for projects, then that's the first place to go, is to download it. And then you'll see what's new. As of Friday, just for you guys, I updated the version on the web to the latest commit in the SVN trunk repository. And so the latest version from the trunk is now being posted, version 4.2. So you have the latest and greatest version to play with this afternoon. OK, so that's what Athena is. So what am I going to tell you about with Athena? So I have 5 lectures. That's not a whole lot, but this is what I decided to do. Today is going to be the introduction to the basic algorithms, and this part I suspect is going to have the most overlap with, say, Patrick Hennebel's lectures and the lectures next week on Flash. Tomorrow I'll talk about grids in grid codes, in particular cylindrical coordinates, and static mesh refinement, and why use a grid. Is a grid a good idea, or should you be using something else other than a grid? I'll have some words to say about that. On Wednesday, I'll talk about adding extra physics. You saw there was lots in there, so I'm going to kind of go through some, not all, but some of the ways you add extra physics to an algorithm like what's in Athena. One particular extra physics that's interesting is radiation hydrodynamics. That's really a very hot topic lately, with lots of research being done in methods for radiation hydrodynamics. That deserves its own lecture. So on Thursday, I'll only talk about how you do radiation hydrodynamics and what's in Athena for radiation hydrodynamics. That is not in the public version, so this proves that it's really under development and that it's really an area of research in the sense that it's not yet stable and mature enough to make it a public version. So I'll tell you what we're doing as a research side in radiation hydrodynamics. Finally, my last lecture will just be some applications and what we're using Athena for. So today is going to be the algorithms in Athena. It's a Godunov scheme, so I'm going to say something about the Godunov algorithm, discretization, Riemann solvers, reconstruction algorithms, integrators, some words about how those algorithms are implemented in Athena, and then finally some tests. So this should be like an interactive lecture, I hope. So if there's something that doesn't make sense to you, please ask a question. I'm happy to stand here for an hour and blab away, but it's usually a lot more enjoyable for me and probably for you as well. If you have questions, don't hesitate to ask them. Okay, so let's start at the beginning. Athena is solving the equations of ideal MHD in conservative form, meaning continuity, momentum, energy, and the induction equation. And as you can see, they're all written in a form that looks like partial time derivative plus divergence of a flux equals 0. So those are definitions of conservation laws, all except the last equation, which instead of having a divergence has a curl, which immediately tells you right away that the discretization you're going to use for the induction equation has to be different than the discretizations you're going to use for all the other equations, because it's not a divergence. It's not a conservation of a volume. It's a conservation of an area. Something special is going to be needed for the last equation. So the discretization involves cell-centered density, total energy E, sum of magnetic, kinetic, and internal, momentum at cell centers, and magnetic fields at the faces of the cells. That's because the natural discretization of the induction equation leads to having fields at face centers, as I'll describe in a minute. And the key thing to take away from this, and the thing you should remember about every single conservative Godunov scheme, is that these are not point-wise values located at the center of cells. These are the volume averages. So rho n of ij, so in 2 dimensions, the value stored at cell center is the integral of the density over the volume of the cell divided by the volume of the cell. That's a very important thing to remember because it determines how you write down the discrete form of the equation. Similarly, the magnetic fields at the faces are not the point-wise value of the field at this location in space, but rather it's the area average of the magnetic field over that face of the cell. Okay, so how do we turn this partial differential equation into a set of algebraic equations? After all, computers can only add and subtract and multiply and divide. It's all they can do, so we have to turn calculus into algebraic operations. How do you do that? You first integrate the equations over the volume of the cells and over a time step dt. And then you use the divergence theorem for the first 3 equations. So the integral over a volume of div f is just the differences of the fluxes on the faces of the cell for using the divergence theorem. So it turns that differential equation into this algebraic equation where you take the difference of the volume average values in time as a discrete representation of the time derivative, and the differences of the fluxes on each of the faces is a discrete representation of the divergence operator for the first three equations. And this is so far is exact. I've turned this into a difference equation, and so far I have not made any approximation yet. This is an exact relationship.
So Jim, isn't this only exact in the limit delta t goes to 0? Right, I mean, haven't you made an approximation in discretized time problem, not the space?
But it's always true that at some advanced time minus the old time divided by delta t, yeah, so in the limit of delta t goes to 0 for the time derivative, yes, that's right. For the spatial side of things, that remains exact. That's right. That's right. Good. Question. Excellent. I like questions. So as a matter of definition, you see this is where these volume and area averages come out. You know, by definition, we said that this quantity u at n I, j, k was this volume integral of the function u, the continuous function u of x, y, whatever what that was, density, momentum, whatever. It was integrated over the volume of the cell, and we stored that integral value, and then we could turn into those discrete forms. And similarly, these fluxes are integrals over the faces and time, so that the time and area averaged flux of each of the conserved quantities through the faces. So in order for that equation to be exact, this has to be the definitions of u and fluxes. That's why it's important to remember that we're dealing with volume averages. So what do we do with the induction equation? That one's a little bit different, I said. Well, that's because it involves a curl operator, not divergence. And so when you take the integral of the curl, it's natural to use Stokes' theorem. And that turns the integral of the curl operator into the line integral around the edges. And so the obvious discrete representation of the magnetic field involves the differences of the magnetic field, area average magnetic field at each face, plus the sum of the line integral around the edge of the face. So in 2 dimensions, that's 4 faces. And in 3 dimensions, we have 3 equations, each of which involves a line integral around the edge. So that leads to this discrete representation of the magnetic field at face centers, because we're going to use line integrals to represent the fluxes or the change of in time of those quantities. And again, this is exact apart from the temporal differencing, and no approximation have been made. And moreover, these equations automatically satisfy one of the constraint equations, one of Maxwell's equations, that div b should be 0. That is to say, if I take the discrete representation of div b at the new time n plus 1, and I calculate what it is algebraically, well, it's going to be the divergence of the b at the old time plus the divergence of all these terms here. And if you go through the algebra on your own, it's rather tedious, but all of these electric fields E on the edges all cancel away pairwise, and so they all cancel to 0. And so the divergence of the magnetic field at the advanced time is exactly equal to the divergence of the magnetic field at the old time. So if you put a magnetic field in initially that had div b equals 0, it's always going to stay div b equals 0. I don't have to do anything special. There's no cleaning required, no other equations needed. It just falls out absolutely naturally, discretization. That's because this is the conservative discretization of the magnetic field. The div b constraint says that magnetic flux is conserved. That's what it means. So if you have a conservative discretization of the induction equation, you'll conserve magnetic flux and you'll automatically keep div equals 0. That's the great advantage of this discretization form, is that it keeps div equals 0 to machine precision. So once again, for complete question, good.
You mentioned that earlier that you include moment dissipation and other
Yes.
resistance effects.
Right.
Does that change induction equation and how you should do this treatment?
Yes, absolutely. So we would have to add more equations, more terms, to the equations if you want to do, say, resistive MHD. These are the ideal MHD equations in which we're assuming the conductivity is infinite and the resistivity is 0. If you wanted to add resistivity, you have to add a term which looks like A to J, the resistivity component times the current. And then you would have to add extra terms to these equations. And the way you would do that, I'll discuss this on Wednesday, I think it is you have to make sure that the current is at the cell edges, and that you difference the current in just the same way as you difference the electric fields. You take a line integral around the edge of the current to update the magnetic field. That way you continue to guarantee that div equals 0. So whenever you add a new term to the induction equation, you want to do it in a way that keeps div equals 0, which means you have to difference it in the same kind of way with this electric field. So for all these physical effects, viscosity, resistivity, you have to add more terms, makes the discretization more complicated. So I'll talk about that on Wednesday. Okay, good. Question 2. So again, just to sort of catalog everything, in those former equations, the magnetic field is this area average quantity, and these electric fields located at cell edges are a line and time average of the electric fields. And so just to sort of put it all together, the discretization used by Athena and many other Godunov schemes for astrophysical MHD have the conserved quantity U. So U is a vector of the conserved variables mass, momentum, energy. It's located at cell centers. It's the volume averaged value stored at cell centers. And in Athena, the magnetic field is the area averaged components at cell faces. Not every other Godunov scheme uses the staggered grid for the magnetic field, but this is what Athena uses. And then the fluxes that are used to update these conserved quantities are the following. The F, G, and H, each of the fluxes in the X, Y, Z direction for the cell-centered conserved variables are located at cell faces. And the electric fields, the line integrals we're doing for the magnetic fields, they're located at cell edges. So that's very, very simple. So far, straightforward. The only complication in the entire machinery here is how the heck do you calculate these fluxes? If I just knew these fluxes, it's a piece of cake, because you just go back and use those formula we have. It's very, very simple. So the entire heart of the matter is how do you calculate accurate and stable estimates for these time and area and time and line averaged fluxes. And we've got to do this, in a multidimensional way, so we have to compute them all at once. So how do we do it? We use Godunov's method. And so, again, I apologize if this is something you know really well, but sometimes it's useful to see things twice. So here we go. Here's how Athena works. It's a Godunov scheme. So the idea is that, well, I have this set of cell-centered values on a mesh. So suppose I'm a one-dimensional grid, and I have a set of cell-centered values. Let me just treat them as piecewise constant values for the moment. So the value in the cell is just constant. So Q of I minus 1 is the value in the cell I minus 1, and so on. And you notice that at the cell edges, there's a discontinuity because the values don't necessarily have to be the same in every individual cell. And so if you treated this as an analytic problem, suppose the solution really was the stepwise profile of the quantity Q, what would happen? Well, at time equals 0, there'd be discontinuity, and so you would launch waves from those discontinuities. The fluid here, say this is pressure, would be a little bit higher pressure than here, would launch a wave into cell I, and there'd be a rarefaction that goes back into I minus 1. Similarly, the wave would go the opposite direction here. And so at some later time, the profiles would look like this. Here is the piecewise constant value here, a rarefaction, a shock wave, a shock going the other way, and a rarefaction, and so on and so forth. And if I just knew this exact line here, then all I have to do is integrate under the curve, because that's the definition of these quantities U, is the volume average values. I just integrate this curve here in this cell here, and I would know what the new value of the cell-centered quantity be at time n plus 1. Fine. That's absolutely well-defined mathematically. It's formally exactly what you should do. But of course, it sounds extremely difficult because I have to calculate this ugly-looking curve, and I have to do this integral under the curve to calculate the advance time. But of course, it turns out you don't need to do that. The conservation laws save you. They tell you that you don't really need to know what this curve looks like, because whatever passes through this dashed line, whatever flux of material goes from this cell to this cell, has to be exactly the same. Whatever mass leaves this cell has to go into that cell. I don't need to calculate the area in the curve. All I need to know is how much mass for this is that travels from one side to the other. It's just whatever mass goes through that dashed line. All I need to know is the fluxes on the dashed lines. And so what I need to do is solve the Riemann problem and calculate the solution along the dashed line, the x equals 0 line in the space-time here. If I just know, I don't need to know the rarefaction fans. I don't care what the shape of the rarefaction fans are. I don't care anything about the details of the solution. I just need to know what the quantities are along this line x equals 0. And if I know that, I can calculate the flux. And if I have the flux, then I can just update the solution in one dimension. I can calculate immediately what the flux is. So the whole point of a Riemann solver is to calculate the quantities along the line x equals 0. You don't really care what the rest of the profile looks like as long as you get an accurate estimate for what the solution is along x equals 0. Okay, so we're going to use a Riemann solver to do that. And there's many, many different ways to do this. Of course, you could use an exact Riemann solver, which gives you the exact solution. That is to say, it would give you the exact profiles of every wave that's produced in the interaction. But as I said, you don't really need that. You can use an approximate solver as long as it gives you an accurate estimate. So with ideal gases in hydrodynamics, it's usually possible to build an exact solver that's fairly efficient, easy to, computationally efficient. But in MHD, that's really quite difficult. Exact solvers are possible, it's just that they're very, very expensive. And you don't want to be solving a very expensive Riemann solver at every interface at every time step. And so some kind of approximate solver is needed. And why is MHD so much difficult? Because this gets back to the physics, because the physics of MHD is much richer. In MHD, there are many more wave families. In hydrodynamics, there's only one, right? What's the only wave family in hydrodynamics? Sound waves. Thank you. I thought, why not? In MHD, you have two compressible modes, magnetosonic waves, the fast and slow, plus you have an incompressible mode, the Alfvén wave. So you replace sound waves with these three other wave families. And what's worse is that sometimes these modes can be degenerate. Instead of having three distinct eigenvalues to the linearized system, there's only two, because two of the wave families can be degenerate. For example, the Alfvén speed could be exactly equal to either the fast or slow speed, depending on the direction of the wave vector in the magnetic field and so on. And so this makes solving the Riemann problem exactly very, very difficult. So in practice, every code that I know that does MHD as a Godunov scheme uses an approximate Riemann solver. So what are the approximate Riemann solvers that people use? Here's a couple of them. There are many, many more, but here's some of them that are the most popular. Rho's method is a very popular solver because it keeps all 7 characteristics in the problem, but it treats them all as a simple wave, as a discontinuity. So it doesn't have any rarefaction fans. It just treats them as rarefaction shocks. Completely unphysical. That would never happen in a real fluid, but it doesn't matter because I don't care what the profile of it is. I just need to know the solution at x equals 0, and Rho's solver gives you the right jumps across all of the waves in the solution, and so that's good enough. So Rho's method is one way. And there's sort of green points are the points in favor, and the red points are the points in the bad points of these solvers. The bad points of Rho's solver is that it treats rarefactions as discontinuities. And so if you have a very strong rarefaction in some cell at some time, Rho's solver will also often return an unphysical state. It will think that the jump across the interface should lead to a negative pressure. And so it'll return a negative pressure as an intermediate state. That's no good. So instead, people also like things like the HLLE, Harton, Lax, Van Leer, supplemented by Einfalt method. It only keeps the fastest and the fastest wave speed in each direction. So one mode in each direction, one intermediate state. So it makes it very, very simple. There's only one intermediate state to compute. It's positive definite, can never return a negative pressure, but it's very, very diffusive because it doesn't keep the rest of the wave characteristics in there. And then these are being improved with so-called HLC, HLD methods. I'm probably getting into too much detail here, so I'm going to just, if you want to know more about these, there's a whole papers written on these different solvers. Athena has them all implemented. You can just configure it to try each of these different solvers if you want. If you want to know how Rho solver compares to HLD, you can just run the test yourself and see how it works. But schematically, what are we doing when we make these different solvers? Here's the exact solution for some Riemann problem. a shock wave, a contact, and a rarefaction. This resulted from some choice of left and right states at time equals 0, generated these characteristics, and we wanted to know the solution along the dashed line. The row solver would replace the rarefaction with a discontinuity, a rarefaction shock. And the HLLE solver would remove the contact discontinuity and produce only one intermediate state between the left and right states. And they're all equally good for this solution because along x equals 0, they all give exactly the same result. And so any one of these solvers would be just as good as any other one. And these are much, much cheaper than the exact solver, so that's why they're used. Okay, so that's the Riemann solver. That's how you compute the fluxes. But go back to what the way I described this method as considering the interaction of piecewise constant states. We're going to have to improve that because that also is a very poor description of the actual spatial structure of what the fluid is doing. And so to get around that, you need higher order reconstruction. Rather than treating the piecewise constant values in the cell, instead we have to fit piecewise polynomials to the cell. You can either fit linear functions into the cell, and then the discontinuity at each cell edge is just the difference between the interpolation segments in each cell. So the left and right states that go to the Riemann solver are this small difference instead of the much larger difference that we predicted by piecewise constant cells. You can use piecewise linear, you can use piecewise parabolic. You can fit parabola to each of the cells, leading to a third order interpolation algorithm, piecewise parabolic. So in fact, all of these codes start from papers written in the 70s and 80s, codes that involve PLM for the piecewise linear method, which involve piecewise linear reconstruction, and PPM for the piecewise parabolic method. PPM is one of the most popular and successful Godunov schemes for doing hydrodynamics. And essentially, Athena is an extension of PPM to MHD. We take exactly the same formulations as what PPM uses for hydrodynamics, and we extend them to MHD. And so piecewise parabolic interpolation is an option here. I won't get much into the details of the reconstruction, but something called, one important concept is to never introduce a new extrema. You can never have an interpolation which leads to a value which is larger than the neighboring cell-centered values. If you do that, your method will be oscillatory. You'll introduce very, very short wavelength ringing in the solution. It can be unstable, and so your method has to not allow new extrema in interpolation. It has to be so-called TVD for total variation diminishing. And so there's a lot of machinery introduced in the reconstruction to prevent that. In fact, the reconstruction is one of the most complicated parts of the algorithm to do the TVD reconstruction for MHD correctly. But I'm not going to get into those details. So we've discussed Riemann solvers and reconstruction, the heart of the method. But that's only for 1D. How do you do multidimensional integration? For hydrodynamics, a popular way is to use something called directional splitting. You solve the equations in the x direction, you update the solutions from all the fluxes in the x direction, assuming there's no fluxes in the y, and then you go back and you solve the equations in the y direction, assuming everything's constant in x, or not evolving in x, and then you calculate all the fluxes in the y and evolve in the y. That's an extremely popular method. It's called Strang splitting. Strang splitting is a way of combining those x and y sweeps in a way that's second order accurate. But that doesn't work for MHD. You cannot do that for MHD. Why not? Because you're not allowed to update components of the magnetic field piecewise. You can't update in the x direction the y and z components of the magnetic field. After all, in 1D, the x component of the magnetic field is non-evolving. That's the assumption of 1D MHD. Bx is fixed in time. So you're not allowed to evolve by and bz, but keep bx fixed during an x sweep because you'll violate div b equals 0 at the end. There's no way you can keep div b equals 0 if you change two of the components of b, but not the third one. So you'll violate div b equals 0. When you do the y sweep, you're now calculating fluxes from a solution which don't no longer obey div b equals 0. You're adding unphysical forces. You do it again in the z sweep in 3D, then you're just continuously adding more and more unphysical forces to the flow. So you can't update the magnetic field in this piecewise fashion. You have to do it all at once to do MHD. This is a point that took a long time, I think, for people to accept, and I'm not sure everyone still accepts it, but it's really quite simple. I mean, I just don't see any way around it. You either live with div b error, or you have to use an unsplit integrator. So we don't want any div B error, so we're going to use an unsplit integrator. How do we do an unsplit integrator? Well, the simplest integrator we have is something we call the Van Leer integrator. It's based on the so-called Mussel-Hancock method. It's very, very simple. You just calculate first-order fluxes at each interface, meaning use piecewise constant values to calculate left and right states, solve the Riemann problem, update the entire mesh in 3 dimensions using all the states to calculate the fluxes. You only advance for half a time step, delta t over 2. This gives you a predicted solution, first-order accurate solution predicted to delta t over 2. You then go back and you reconstruct this predicted solution using second-order interpolation to get the left and right states at each cell face. You then solve the Riemann problem again, calculate new fluxes, and update the whole thing, the full time step. So it's a predictor-corrector method. You predict a solution, you then use that predicted solution to correct for a full time step. This is a single-step update, keeps div b equals 0. Second-order accurate. That's the Van Leer unsplit integrator. There's also more complicated things. For example, the corner transport upwind method. So this took Tom Gardner and I probably 4 years to figure out how to do this for MHD. This algorithm was introduced by Colella in 1990 for doing unsplit hydrodynamics. And doing it for MHD involves a lot of machinations, a lot of steps. It is more accurate if you do tests. It's more accurate than the Van Leer integrator. It's less diffusive. Still only second order accurate, but it's less diffusive. But it's a lot more complicated and a lot more difficult to extend with more physics. I mention it because it's there. If you want to know about it, you can learn more about it from the papers. But I think I'm not going to really explain it very well here in such a short time. So there it is. If you're just doing ideal MHD, CTU is great. If you want to extend it to relativistic MHD, it's extremely difficult to extend it with all that extra physics. And so CTU is not available for all the physics options that are in Athena. Van Leer is often the one we choose because it's so much easier. OK, we're almost there. We just got a few more steps left. We've got Riemann solvers, we've got reconstruction, we've got unsplit integrators. The one final step, which cost Tom Gardner and I another couple of years to figure out, was how you get the electric fields at cell corners as you need for CT. That is to say, we've got these cell-centered values. We're solving Riemann problems at the faces to get fluxes. That includes electric fields. After all, the fluxes of the magnetic field are just the electric field. So our Riemann solvers are going to return the area averaged and time averaged electric field at cell faces. But that's not what we needed to evolve the magnetic field, remember? We needed the values at the corners of the cells, not the faces, to evolve the magnetic field. Somehow we have to get these area and these face-centered electric fields to a corner. Now the obvious thing to do is that to take these 4 values and average them together, just algebraically average them together to get the electric field at the corner. But it turns out that that breaks upwinding of the method. As it doesn't reduce to the equivalent 1D algorithm if you have plane parallel flow. There's many sort of simple things, simple ways you can show that's not the right thing to do. So instead, we need something more complicated that Tom and I came up with. It involves upwinding these electric fields to the corner based on the fluid flow direction given by the density flux at the cell faces. So again, I won't say much about it, but there's this paper here will describe in great detail how we calculate the electric fields at the corner. Something special is needed to make the electric field at the corner. And a way to see that is to do this advection of a field loop test. Just take a loop of magnetic field, solve an advection problem, and make this magnetic field extremely weak, so the ratio of gas pressure to magnetic pressure is 1,000,000, and then just advect. So this is not going to evolve magnetically. The field is so weak, it's just a passive quantity that follows the fluid. If you just do arithmetic averaging of the magnetic field, arithmetic averaging of the electric fields to the cell corners, you see it's oscillatory. You get this ringing in this basically at 45 degrees to the mesh. But if you do this upwinding, you can make that go away. This upwinding is the necessary step to keep the scheme non-oscillatory for updating the magnetic field in the Gauss scheme with CT. Yep.
Sorry to take you back but
Sure.
you need the electric field in the corner for what part exactly when you were doing the...
Yep, good question. It's indeed, let me go back to here. All right, so our magnetic fields are face-centered area averages, right? And to evolve them, we need the electric field at the corners of the cell in 3 dimensions.
The corners of the cell, you mean the edge?
At the edges, right? So, as in this picture. So E here is the electric field. So it's right at the corner of each cell, along the line that's joining the grid,
Okay, so
right?
you don't mean the actual dot that's the corner.
Right. Yes, I'm sorry, my and language is not being very. I don't mean corner as in there, where all the lines join. So what's the right? I might call that a vertex, maybe, corner. I mean this line, the line. Sorry if that was confusing. Good. You see, don't be confused. Ask questions. Good. So the point is that the Riemann solver returns this flux F. Of course, in G and H in the other directions. I somehow have to get F to the corners, lines, edges. And I got to do that in all these different directions. And that's where this upwinding scheme of Gardner and Stone is necessary. You can't just average them together. Okay, so now we're done. Now we're going to talk about details, I guess. And some of them are important, some of them not so important. I mentioned this because there was a lot of literature on this. These Godunov schemes are known to have what's known as the carbuncle instability. If you run a shock wave, a very, very strong discontinuity, aligned exactly with the mesh, you find the shock wave generates all this noise along the edge. So it's unstable to perturbations when the shock is exactly along the mesh. This seems bad. Well, actually, this is a representation of how good the method is. The problem is that the method has too little dissipation. It treats shock waves so well that it does not have enough dissipation in the transverse direction to prevent growth of numerical perturbations in the shock front as it propagates along the mesh. And so there's a very, very simple fix. You have to add more dissipation. I mean, it's nice to have a numerical scheme where you have to add a little bit of dissipation because it's not dissipative enough. Most schemes, you're fighting dissipation. You're trying to make it less and less dissipative. Here's a scheme where you have to add more dissipation to fix it. So it's very straightforward using something called H correction. You almost never need this. It's almost only ever important when you're doing test problems because in any general flow, you almost never have shock waves always aligned exactly with the mesh. They're all over the place. So, and the tests I'll show you later, I don't even use this carbuncle instability fix, but it's there if you ever want to use it. So now we get into implementation details. How do you implement this and how do you, for example, handle boundary conditions? Obviously an important issue for any problem you're solving with hyperbolic systems. So the way we solve boundary conditions is, I think, exactly the same way as everybody else is using grid codes. We define something called ghost cells. They are a set of extra cells beyond the edge of the active mesh. The solid black line represents the edge of the computational domain where we're actually solving the equations. The little dots are representing cells inside the computational domain. We copy the solution from the active cells to the ghost cells according to different kinds of boundary conditions. If they're reflecting, we reflect the quantities. So the normal component of the velocity will be reflected and all the other quantities will just be copied. We can have periodic boundary conditions where these values are copied from the other side of the mesh. We can have outflow boundary conditions where you just project the quantities either with just a piecewise constant value or maybe even use linear interpolation depending on what you want to use. So you have complete freedom in deciding how you want to set these ghost cells, and that's the way you do it. With PPM, you need 3 cells for the piecewise parabolic interpolation, but with an unsplit integrator you have to add 1 more with MHD in a staggered mesh. So Athena requires at least 4 ghost cells if you're doing 3rd order MHD. If you're only doing 2nd order hydrodynamics, you can get away with less, but with 3rd order MHD, you have to have at least 4. The code, sort of by default sets that already. The boundary, because this is, yeah, go ahead.
Why are 4 need, like, what principle of stability makes it so that you need 4 rather than a lesser number?
you need 3 because with piecewise parabolic interpolation, the difference molecule, the number of cells that you need to define the parabola extends 3 on each side. So if you're standing in one cell, and I'm trying to calculate left and right states by using piecewise parabolic interpolation, in order to set all the limiters on the slopes, I need 3 more cells on either side of me. So that's the first 3, just to calculate the interpolation parabola. I need 1 more because I have a staggered mesh, and so the interpolation of the magnetic field in the faces is staggered by 1 cell. And moreover, I'm using these CTU and Van Leer unsplit integrators, which involve a predict correct, and then a predict step, and then a correct step. So that adds, I have to evolve the magnetic field in the ghost cells in order to have a solution which is accurate for the final update, and so that leads to 4 cells. Okay. It won't be unstable if you don't have enough ghost cells. It'll just be wrong. I mean, you won't have enough points to actually interpolate things, and you just get the completely wrong solution, which then may be unstable. You don't know, but you know, it's very easy to tell when you don't have the right number of ghost cells because you'll see features of the boundaries which shouldn't be there. Okay, so Athena is, you know, underlying the basic numerical algorithms, the basic applied math under the code is the same as many, many other codes. Some differences in that we use unsplit integrators, we use staggered meshes, but the features are very, very similar to other codes. It's the implementation where codes differ. It's how you actually put that into a computer program that differ. And so Athena is just one implementation, and there are many, many more. You've heard of one Ramses, there's others, many, many others. So what does Athena consist of? There's 2 versions, the C version and the Fortran 90 version. The Fortran 90 version hasn't been updated in quite a while, so it's fallen quite far behind. So by far the most capable version is the C version. It's very, very modular. So that makes changing things very, very easy. All the reconstruction algorithms can be swapped in and out easily. It's very easy to use. You can tell me whether that's true or not. You're going to find out yourself if you do the homework problems, because you'll have to install, configure, run it. You can see for yourself whether or not it's easy to use. The main key for that is don't use external libraries unless you absolutely have to. My mantra is never make a code depend on another library, because then you just have to install that other library, or else you have to rely on somebody else to install that library for you on the machine, unless you absolutely have to have it. To do MHD on a single processor, you don't need any other libraries. You can write a code that's completely independent of all libraries, so Athena doesn't require anything. If you want to do MPI, then of course, yes, you're going to need the MPI. I'm not going to write an MPI library. You're going to have the MPI library installed. There's one library you're going to need if you're going to do that. If you're going to do Fourier transforms, you're going to do self-gravity with FFTs, then you're going to need an FFT library, just because that's better than trying to write your own. So of course, you know, you can build extra capability that requires other libraries. I'm not saying don't use other libraries. Absolutely use other libraries if they save you work. But just don't build something that requires a library when it doesn't need to require a library. So that's one sort of, you can see in one of my soapbox rants. Another thing is portability. Don't ever use language extensions, as convenient as they may seem. They'll always come back and bite you because you'll try to compile it on another machine that doesn't have, or most importantly, the language, that compiler will go away. You'll try a new compiler. It doesn't have those extensions in it. Strict adherence to ANSI standards is another one of my soapbox rants, because that way it'll compile and run on anything. And we've tried to make that true of Athena as much as possible.
Do all the various compilers installed on the various machines?
I'm sorry?
Do all the various compilers you're likely to encounter support the ANSI standard?
Yes. I mean, otherwise they wouldn't, you know, absolutely, they all support the ANSI standard. Then they come with extra additional features.
I don't know if that's true in C++. I've had experience with compilers failing to support the ANSI with
Right.
C++ compilers that fail to support the ANSI.
Well, I think then you're just making my point. Because if the compiler doesn't even support the ANSI standard, it's extremely unlikely to support any feature beyond the standard that you're trying to build into your code. So, of course, you know, there's always problems potentially with compilers and so on. But the best you can do is, you know, follow what they tell you in the books. you know, if you know, you write ANSI code, and if the compiler doesn't solve, so the GNU compilers I've never ever had a problem with, for example, and they're available almost everywhere. Even the C++ compiler, never had a problem with it for it.
Sorry for the ignorant question, but what's the ANSI standard?
So it's the what does ANSI stand for even? It's think of it as this governing body that, you know, kind of, you know, somebody else has a better explanation?
What is it? American National Standards.
American National Standards Institute. So even after you said it, I'm not sure what that means, but it's some, you know, uber body that's supposed to set rules that every vendor is supposed to adopt to make things, you know, I could tell you all kinds, I'm old enough now to tell you stories about the days when, heck, you know, machines weren't even bit compatible, let alone, you know, language compatible. So at least things are much, much better now. Most compilers should at least follow this set of rules set by ANSI. And you can read these rules. You know, if you write code in this particular, using these particular features, it'll always work with any compiler. I'm not sure it's the best explanation, but think of it as the common set of rules that all vendors try to make their compilers agree to.
What is the C language? If you want to call it a C compiler, these are the following, you know, you must support the following.
That's correct.
The following syntax.
Right. Pointers have to work this way. You must have these kind of variables allowed, and so on and so forth. So for example, in C, there's no native complex variable type. That's a great oversight, because complex variables are extremely useful in computational physics. Many, many compilers support complex variables. I say don't use them. I say write your own complex variable structure in C and use that. Even though that's probably a bad example, because by now most compilers support that, I still think that it's best to stick to the most basic description of language. Okay, what else am I going to say? The good thing is that these methods are extremely parallelizable. You have gazillions of cells. You're going to do exactly the same operation in every single one of these cells. That's massively parallelizable. You just break the cells up into groups, into chunks, and you update each chunk on a single processor. And since they're single-step unsplit methods, you just have to swap the boundary conditions between the chunks once per time step. So there's one communication call required per time step, and the rest is all computation. So that makes it extremely easy to parallelize. Question?
That's not true with SMR.
In the way that I do SMR, it is almost true. There's one more extra step with SMR, but I'll try to convince you that even that doesn't cost you very much for doing MPI, it turns out. But you're right. AMR, yes, that's true. AMR is that's definitely not true. AMR is quite a bit more complicated. But in just talking about the basic ideal MHD in a single grid, it's very, very parallelizable. So I use configure to handle all the different options that are in Athena. Whenever you want to set up a problem, the first command you type is configure with a bunch of options, with package equals a name, or with enable some feature. And if you just type Athena-C, it'll tell you all the different configure options that are available. And they control all the physics and algorithmic options. So for example, the problem is to run a new problem, you write a C function that sets up the initial conditions, and you give that function a name, and you tell the code that name through the configure. You say dash dash with problem equal the name of the file you just wrote, and then the code knows to link that file during compilation and run it. So you can easily switch from one problem to another. The gas properties means MHD or hydrodynamics or special relativistic MHD or hydrodynamics. You can choose one of the others at the configure step. Equation of state, adiabatic or isothermal. The scalars, that's the number of passive scalars I told you about you can carry around. Whether you want to have self-gravity turned on, resistivity, viscosity, thermal conduction. It's all handled at the configure step. It's useful because then when you actually compile the code, it contains only the algorithms you need for that problem, and so it's small and efficient and doesn't have a lot of things. Like, for example, if you want to do if you want to do hydrodynamics, and if you don't have this kind of configure step, you may have magnetic fields you set to 0. It's a very inefficient way of doing MHD with all these arrays with all zeros being evolved with 0 times 0. So instead, it is all handled through configure. Parallelization is done with MPI via domain decomposition, as I've mentioned. Balancing workload is easy because the flops per zone is fixed, except for when you're doing AMR. See, for right now, it seems like the ideal block size is around 64 cubed. That gives you about the right amount of work per single processor compared to how much time you're swapping data. Let's see, you can overlap working communication. We don't actually do that. We tried using OpenMP. Doesn't help performance at all on the current generation of multi-core processors. That's changing very quickly with the Intel 5. When you have 62 of the cores on a single processor, then you're going to have to use OpenMP to be able to use this. That's going to change soon. I won't talk about the FFT parallelization. One trick for writing your own code on these multi-core processors is to group MPI processes together. So most processors today consist of more than one core on the same chip. So they can communicate with each other using OpenMP, using shared memory. So if you're going to break up your grid into all these MPI blocks, you want these 4 blocks to be together on the same processor, because then all the communication between them on each cell face is all local, on chip, and is faster than using the communication network. So one way to group all this MPI blocks is into another 3D array of blocks. And so the highest resolution simulation I've seen done to date is on Blue Waters using PPM code written by Paul Woodward. Got a sustained performance of over 1.5 petaflops using 700,000 cores on Blue Waters. And he had to do this. In order to get that kind of performance, you have to group the processors onto the chip like this. So it's an interesting trick. And with Athena, because it's straightforward, simple, explicit differencing, yeah, we get pretty good scaling. This is the efficiency, the performance of per core compared to the performance of the code running on a single processor. So it starts off at 1. So if I run the code in one processor, I get the performance of one processor. And if I run it up to about 64,000 cores, the black line is no static mesh refinement. It stays 95% efficient, which is pretty good on 64,000 cores. And even when you add static mesh refinement, it only goes down to 85% efficient, even though I'm doing 64,000 cores. So I still think that's pretty good scaling. When I have 4 levels of refinement on 64,000 cores, it's still running at 85% efficiency. It still works pretty well, just because that's the way these MHD algorithms are so straightforward and simple. We use this track website combined with SVN to do the, we use SVN as a code repository, and track is I showed you the page before. You can go and have a look at that. I'm kind of running out of time here, so I think I'm going to skip on to a couple of tests. So there's many, many papers written on tests, and again, you can look at the web pages. I have an extensive set of test pages on that track site. You can go through the entire test suite if you want. But I'll show you a couple. And I always think one of the most useful is linear wave convergence. It finds bugs for you very easily because it's looking for a very small error. You're looking for a very, very small effect. If you've got a bug somewhere in your code, it shows up immediately because you won't get convergence of the solution. So this is just a matter of setting up a linear mode of each of the MHD wave families, propagating it across the mesh with periodic boundary conditions. Since the solution is analytic, you evolve it for some number of wave periods. Then you take the numerical solution, compare it to the analytic solution, calculate the exact error in the solution, and then plot that error versus number of cells in each dimension. And you should get the error decreasing, for a second order scheme, it should be decreasing at n squared, and you can see it does. For each of the different algorithms and different wave modes in Athena, you get second order convergence. And this is, when you're doing a grid code, it's important to do these tests in full 3 dimensions with the wave vector at some arbitrary angle to the mesh, not parallel to any of the directions, because otherwise the algorithm simplifies to where there's no transverse gradients. If you've got a bug in the y direction, you won't know it if you're doing waves only in the x direction. And similarly, you don't want to do it at 45 degrees because then the x and y fluxes are exactly equal, and that can hide bugs. If you happen to have an x and a y swapped, you wouldn't know because they're the same value anyways. So you've got to run it at some weird angle to the mesh where there's no symmetry in the problem at all, and then calculate this error. That's the only fair way to do it with an MHD. The same way when you're doing with SPH, you should be doing it in full 3D with all the particles so that it's a completely general test in the way you would run the problem in run the code in an actual problem. it's important to run this problem with SMR to make sure it works, and that I'll show that later. Exactly. So you're doing adaptive mesh refinement. You know, just arbitrarily throw down a bunch of meshes in some random locations and then propagate a wave across it. And if you get a problem with it, you've got a bug in your code somewhere. Riemann problems are a classic way of testing these codes. There's this Ruin-Jones paper, which is now famous for presenting a whole bunch of analytic solutions for MHD Riemann problems. I won't show you that. I'm going to jump ahead to some more interesting things. Here's an interesting test taken from Liska and Wendroff, an interesting paper on testing hydrocodes. They just took 5 or 6 hydrocodes, you know, they were given to them, and they just blindly ran them on exactly the same tests as they were written to see how well they did. And here's one of the test problems they have. They have this high density, high pressure region in a box with reflecting walls and this low pressure, low density region in the corner. These are the conditions for the so-called SOD shock tube. So it's going to launch a shock and a rarefaction. They're going to interact in interesting ways. You get a double Mach reflection at each edge where the shock wave interacts with the reflecting walls. And you get a rather complicated, interesting evolution. It's worth having fun. You know, if you want to learn some fluid dynamics and shock dynamics, it's fun to watch this kind of evolution where you see the shock wave, it's reflected, goes off, it reflects again. You get this little double Mach reflection, which generated a vortex. The vortex combined. Now you get a jet along the wall. I mean, there's tremendously complicated dynamics going on here. At later times, you get something called the Rickmeyer-Meshkov instability, because there's a contact discontinuity here, which is being overrun by shock waves. That launches Rickmeyer-Meshkov instability along all these little fingers and rolls, or RM instability. You see that these vortices have rolled up into a cage pair at the top here. So, you know, it's worth running this with different codes just to see how, I'm sorry, the colors have completely washed out. That looks very boring, but trust me, configure and run this problem yourself and watch the movie that the code will generate for you. It only takes you a few minutes to run it, and watch the movie yourself. It's fascinating. It's amazing stuff goes on with this test problem. And it's a good test because you don't get this jet unless you maintain symmetry. If you do this problem with a directionally split method, x, y, x, y, you will not get that jet down the axis because you'll break symmetry. It relies on symmetry. So that's kind of a useful side effect of having to use an unsplit integrator for MHD. You get this symmetry preserving solution sort of automatically. And then to show shocks in MHD, let's do the Rickmeyer-Meshkov instability. We'll do spherical blast waves. Again, there's no analytic solution to this. There's no known solution to compare to. You're just doing this to make sure things are stable and that the solutions are sensible. So this is periodic boundary conditions in a non-square rectangular domain. You put in a very, very, very high pressure region initially, so you get a very, very strong pressure jump, 1,000 to 1 pressure jump, and then you allow the shock wave and rarefactions to propagate. And you do this with hydro and then with a magnetic field at the edge. This was a difficult test because with such a large pressure jump and a strong magnetic field, beta less than 1, the code will often crash. A total energy code will often crash with this method. And so doing it is useful as a useful test of the robustness of the method. So here's the hydro problem. Starts off with a spherical blast wave in the middle. I'll just stop it there. So there's your nice. It's a good check that your code holds. You can get, you know, with a Cartesian mesh, you get a very, very nice spherical symmetry. No grid effects that you can see at all in that blast wave. So that's a nice test. The contact is already showing some grid effects, however. This oscillations are due to the grid. If I do this with MHD, well, the zeroth order thing that happens is that it's no longer spherical. So we start learning some MHD here because the wave speed perpendicular to the magnetic field is faster than along it. You get a shock wave which is distorted in the transverse direction, and also the contact itself is also distorted. And then you can just let these go, let them run longer. Because of periodic boundary conditions, it's totally unphysical. So this is a supernova going off in interstellar medium with periodic boundary conditions. I challenge you to find one of those somewhere, but this is what it would look like. It would be awfully cool because as the shock wave comes back through, it runs over itself. It runs over the bubble it's made, and that generates these Rickmeyer-Meshkov rolls. And so this kind of shock dynamics is what Godunov schemes are good for. They're very, very good at shock capturing. So if you're doing highly compressible flows, these methods are really, really good. If you do this with MHD, then you find that Rickmeyer-Meshkov has suppressed the boundary. And so, in fact, there was just a recent paper in the last 5 years discussing Rickmeyer-Meshkov and MHD and pointing out that a magnetic field will stop these fingers from growing, but otherwise it just kind of looks the same. Except it's actually not the same, much more distorted along the edge. Okay, so here I'm done. I say that Godunov methods are a very, very good way to do MHD, especially if you're doing problems involving strong shocks. No code is good for everything. And there's always going to be a sweet spot for the use of every code. What's a sweet spot for grid-based MHD codes? It's compressible shock dynamics. That's where they're really, really good. You can use CT. You don't need any kind of divergence cleaning to keep div equals 0. Methods scale extremely well, very simple because they're explicit single-step updates. And this is Athena as it stands now. Right now, there's a new version of Athena coming out, Athena++, written in C++. It's 10 times faster per core by taking very careful note of vectorization on the current generation of cores. You can get much faster performance than the current C code. It has a mixed parallelization to be able to use the Intel Xeon Phi. And in the next couple of years, it's going to involve full GR and relativistic time-dependent radiation transport, as well as AMR. So that's going to be the future of Athena. I think Athena 4.2, which is on the web right now, is a solid code, well tested. It's useful for lots of applications, but in the future, this is where the workhorse of where the research in my group is in Athena++. So I'll stop here.